Okay, up to now, we've been dealing with phases which just have one component, Al2SO5, SiO2, and so on. And we know that in those cases, when you only have one component, that the chemical potential of that component is equal to the free energy of the phase. Now, we know in earth sciences that's a rather unusual circumstance. We've already covered the case of magnesium carbonate, calcium carbonate mixtures in aragonite, and that's the general case. Normally, minerals and fluids, solutions in the earth sciences contain more than one component. This was just our simple way of getting started. So how do we deal with multi-component cases? Well, what is the effect of adding components? In order to consider that, we need to think about this thing called entropy. Now, entropy is basically a measure of the degree of randomness or disorder that there is in our phase or system. So the more disordered a phase, the higher its entropy. So let's take an example. Let's take a system of H2O. So H2O, we know, has three phases. There's ice, there's H2O liquid, and there's steam. So let's consider H2O liquid and think about the randomness in H2O liquid. What do I mean by randomness? Well, let's think about it. Suppose I wanted to know where any one particular molecule was in let's say I had a litre or kilogram of water, and I want to know where any particular molecule is at any one time. Now, that molecule of water, which of course is H2O, with an angle of about 109 degrees between the two hydrogen atoms, that molecule of water is moving around. The one I'm interested in is moving around in my litre of water. So actually putting a finger on it is not very easy. And that means that the water, liquid water, has a certain amount of entropy. And that's entropy, if you like, of translation, associated with motion. But also there's entropy of vibration, because these atoms are vibrating as well. So if I wanted to know where the oxygen was at any moment, it would be difficult to say because these things are vibrating. And also it rotates, so there's entropy of rotation as well. Now, if I cool that liquid down and turn it into ice, all of a sudden things start to get different. In the structure of ice, each molecule has its place and it's fixed in that place. So we lose all of this entropy of translation and all the entropy of rotation. Okay? all we have left is the entropy of vibration. That is, even though the molecules are stuck in the lattice in fixed positions, these bonds keep vibrating. So you'll have some entropy contribution. So ice has a moderate entropy contribution due to vibration of the HO bond. As we go down temperature to the 0 degree of Kelvin, the amplitudes of the vibrations get smaller and smaller and smaller, and eventually, in theory, at 0 they will cease. And entropy becomes 0 at the 0 of absolute 0. So, all right. So fairly obviously, it doesn't take, but it's not too difficult to realise that the entropy of ice, the fixed crystal structure, is less than the entropy of liquid water. Now, if we heat this water up and turn it into steam, we maintain the vibrations. In fact, the vibrations will get more intense because the temperatures are higher. And we gain entropy of rotation and translation, but those entropies are now even bigger because the molecules are going over much greater distances. Okay, so the randomness or disorder associated with steam is much more than the randomness or disorder associated with liquid water, because the molecules have, in a small amount of time, so a fixed amount of time, they'll travel much, much further. The volume of a kilogram of steam is going to be something like 1,400 litres. Left my calculator upstairs. It's going to be something like 12 or 1,400 litres, whereas the volume of a kilogram of water is only 1 litre. Have I got that right? What did I say? Should be about 1,200 litres, yeah, 1,400 litres. Anyway, the point is that steam has the highest entropy because it has all of its entropy of translation. Okay, so now let's consider our solids. We've been talking about solids. So now consider a solid, and let's suppose it's a simple oxide. Magnesium iron oxide. Actually, it's a very important mineral in the Earth because in the lower mantle, magnesium iron oxide is a major phase. It doesn't occur very often in crustal rocks, but it is important in the Earth as a major phase. So what does the entropy of this solid oxide look like? Well, it'll obviously have vibrational entropy. All of the atoms will be in fixed positions in the structure, but there will still be these vibrations that we talked about in the context of H2O. Okay? In addition, there is an additional form of disorder or randomness due to the mixing of the magnesium and iron atoms. Okay, so the magnesium and iron atoms occupy the same positions in the structure. This has got sodium chloride structure, so each magnesium and iron atom is surrounded by 6 oxygens. So those atoms occupy the same positions. So at some temperature, let's suppose let's say for the sake of argument, 1000 degrees K. The magnesium oxygen bonds are vibrating, the iron oxygen bonds are vibrating, giving us some vibrational entropy. But there's an additional contribution to the entropy, and that is the entropy of mixing. And that comes from the fact that if I look in the structure, if I looked at any one particular position in the structure, I would not know whether that was magnesium or iron. There's a certain amount of randomness that's been introduced because these occupy exactly the same position in the structure and they replace one another quite happily. So I've added a certain amount of entropy or randomness by mixing the magnesium and iron together. And so what that does is, because G equals H minus TS, as I increase S by this mixing procedure, I'm obviously going to stabilize the phase even more because of this negative sign. So as that goes up, free energy goes down and the phase becomes more stable. Okay, so what is that what is that entropy of mixing? So let's say for our mixed oxide, we have vibrational entropy plus mixing entropy. And the vibrational contribution is from the end members, from pure and pure MgO. So the pure minerals both have vibrational entropy, and that is inherited when we mix the magnesium and iron oxides together. But in addition to the vibrational entropy, which is inherited from the pure minerals, we also have an entropy contribution due to mixing. So, what is that contribution? All right, so Boltzmann gave us the answer from statistical mechanics. The entropy of mixing is equal to plus K log omega. Okay, now omega is the permutability. Which is the number of different ways I can put the atoms of magnesium and iron into the different positions in the structure. Okay, the number of different ways. So that, which is, as you'll see, is a lot. So let's take, for example, let's just suppose there were only 8. We only were considering a cluster of 8 atoms of magnesium and iron. Then obviously we could put the 8 atoms into our 8 positions in, how many is that? 1, 2, 3, 4, 5, 6, 7. So it could be, let's suppose there were 3 magnesiums and 5 irons. We could put them in as FeMg, 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 Fe, that would be one way. Or make Mg, Fe, and so on. And we could write them all out if we, if we really wanted to. But in this case, of 3 magnesiums and 5 ions, then the permutability is equal to 8, which is the total number of atoms, factorial, over 5 factorial, a number of ions, times 3 factorial, a number of magnesiums. And that equals 8 times 7 times 6 times 5 times 4 times 3 times 2 divided by 5 times 4 times 3 times 2 times 3 times 2. So those go with those. 5 and 4 go here. 3 2s are 6. So there are 56 different ways, 7 times 8, in which we could put those 3 atoms of magnesium and 5 atoms of iron into those 8 positions. Now we're considering a lot more atoms than that, of course. In 1 mole of substance, they're going to be Avogadro's number of positions. 6.02 times 10 to the 23. So let's suppose then that we're interested in the mixing of a mole of substance, which is normally the sort of amount we're considering. So there are Avogadro's number of positions, a grand molecule. There'll be NFE atoms of iron and NMG atoms of magnesium. So the permutability then will equal Avogadro's number factorial divided by NMG factorial and FE factorial. And the entropy of mixing per mole will be Boltzmann's constant times ln Na factorial over NMG factorial and Fe factorial. Now, writing out the factorials are going to take us a heck of a long time, so we won't bother with that. We use Stirling's approximation. Which says that if n is large, which it certainly is in this case, ln of n factorial equals n ln n minus n. Well, that means then that our entry of mixing, make sure you can see that, S mix is equal to K into Na ln Na minus Na minus NFE ln NFE plus NFE minus NMG ln NMG plus NMG. Now, NFE plus NMG is equal to Avogadro's number, so that goes with that. Sorry, that and that goes with that. And what we're going to do now is we're going to separate this into two terms. NFE ln Na plus NMG ln Na minus NFE ln NFE minus NMG ln NMG. We use the properties of logs so A ln y minus A ln x equals A ln y over x. So we use that property, and this becomes k into NFE, sorry, minus NFE ln NFE over Na minus NMG ln NMG over Na so we take the minus outside and divide through here by Na, so equals K minus K times Na, Avogadro's number, remember, into NFE over Na ln NFE over Na plus NMG over Na ln NMG over Na. Now that Boltzmann's constant times Avogadro's number is the gas constant R. And the number of iron atoms divided by the total number of atoms is the mole fraction of iron. So that equals XFE. And the number of magnesium atoms divided by the total number of atoms is the mole fraction of magnesium. So that goes there and there, of course. So F mix is equal minus the gas constant into XFE Ln XFE plus XmG Ln XmG. Okay? So now let's suppose now that we have our mixed crystals and we want to calculate chemical potentials and free energies in our mixed crystals. Well, let's step back for a second. Let's suppose that I have a box of crystals. Let's suppose that here I have a whole bunch of crystals. Blue ones are FeO, pure FeO, and pure MgO. Okay, so I have this box, they're pure crystals. Each of these crystals has vibrational entropy. Right? And I know what the vibrational entropy of the FeOs are, and I know what the vibrational entropies of the MgOs are. Now if I stick these crystals together and heat them up, the magnesium and iron atoms will start to interchange. So we will gain entropy of mixing. And that should be the principal effect of mixing, should simply be the entropy of mixing. In fact, we're going to assume it is for the purposes of this class. It is a dominant factor, certainly for the oxides and minerals like olivine. And we will use that to calculate the effect of mixing on our mixed phases in nature. Okay, so let's write that down. And sketch it on our free energy diagram, just to really make the issue unclear. All right, so our mixed crystal then has entropy of the pure end members, it has enthalpy of the pure end members, and it has entropy of mixing. So let's consider MgFeO and let's suppose it has XFE of FeO and XmG is a mole fraction of MgO. And of course XFE plus XmG equals 1. So the free energy of this mixture is going to equal XFE times the free energy of FeO plus Xmg times the free energy of MgO minus T times the entropy of mixing. Okay, so what I've done is I've just added this enthalpy of mixing term. So I can decompose this into the enthalpy of FeO and the entropy of pure FeO. And I can do the same for that. I can decompose that into the enthalpy of MgO and the entropy of MgO. Alright, so I inherit the vibrational terms from the pure M members. That's still there in the mixed crystal. The atoms are still vibrating in the same way. But now I've added this mixing entropy, which comes from the Boltzmann relationship, by mixing the iron and magnesium together in the structure. So let's write that out a little more fully. Free energy of mixing of the mixture is XFE G FeO plus XMG G MgO minus wherever my permutability went to, here. So minus TS mix, so it's negative of that lot times T. So it's plus RT into XFE ln XFE plus XMG ln XMG. So we can call that, this part, the free energy of the N members, and that part, the free energy of mixing. And how would that look on a free energy diagram? Well, I hope it won't have escaped your notice that these values are less than 1, and the logarithm of a value less than 1 is negative. So this whole term is negative. So the free energy of the mixer is going to decrease due to mixing. All right. So what's this look like on the free energy diagram? Free energy of pure MgO is there. The free energy of FeO will be there. So the N member term is simply something on that line, depending on the composition. So somewhere along that line will be that term. The free energy just due to the values of the N members. And this big free energy of mixing term is negative. So it brings it down like so. And that distance there is the free energy of mixing, which is minus T times the entropy of mixing. And of course, in general, what we want is the chemical potentials. And we get those by drawing a tangent to the free energy curve. Helps if it touches, like so. If that's our composition of interest, it isn't meant to be halfway along, it's meant to be anything. And we know that this intercept is the chemical potential of FeO. That is the chemical potential of MgO. So how do we extract those from this? If you remember, what we needed to do is differentiate the equation of the free energy with respect to one of the M members and multiply by the length of that line, or the length of that line, depending on which M member we want. So let's differentiate with respect to xmg. And remember that xFe equals 1 minus xmg. So let's make that substitution first. One minus xmg gFeO plus xmg gMgO plus RT into 1 minus xmg ln 1 minus xmg plus xmg ln xmg. Okay, so we differentiate with respect to xmg. So d by dx of 1 is 0, d by dx of x is minus 1, of minus x is minus 1, so that's minus gFeO. d by dx of x is 1, so plus gMgO. Plus RT into d by dx of minus x is minus 1, so ln 1 minus xmg. Sorry, that's minus. Minus 1 minus, differentiating by parts. Plus ln xmg plus xmg over xmg. So that's plus 1, that's minus 1, so that disappears. And then what we need to do is we need to multiply that by 1 minus x mg and add to g. if you recall from the first lecture. We showed that the chemical potential of, let's say, MgO would equal G plus 1 minus xmg dg by the xmg. So we take the derivative multiplied by 1 minus x and we add it to the free energy of the mixture up here. So we have a term in GFEO, so it's GFEO times 1 minus xmg negative plus 1 minus xmg GFEO. That comes from there. 1 minus x times that, and we add them together, so that term disappears. One minus x MgO times G of MgO plus xmg GMgO. So we add that. So 1 minus x plus xmg. So that's obviously just 1. And then we add plus RT into 1 minus xmg ln 1 minus xmg minus 1 minus xmg ln 1 minus xmg plus RT xmg ln xmg plus 1 minus x times ln xmg from here. So that term goes with that. And we end up with a very simple result that mu MgO equals G MgO. So that's the pure phase from here. Plus RT ln xmg. That's a very important result. So all we've done is we've changed the chemical potential from the value for pure MgO by adding RT ln x. Okay? And you can see that here. That distance is RT ln xFE. The difference between G of FeO and mu of FeO. And I'll just move that G a little bit, and that distance there is RT ln xmg. Okay. Now we come to an important thermodynamic definition, which is that mu of I is mu 0 of I plus RT ln activity of I. Okay, so this is the standard state chemical potential. And this is called the activity. And in words, activity is regarded as being a thermodynamic expression of concentration, which of course in this correlation between those two expressions is quite clear. So then, if we take our standard state chemical potential is as the free energy of the pure phase at the pressure and temperature of interest, okay, so if mu I is equal to the free energy of MgO pure, then the activity of MgO is simply equal to its mole fraction. Okay? Now let's consider a slightly more complicated case. I'm going to have to run on about a few minutes. I normally would have done this in the practical, but I'm going to do it now. Let's suppose we take olivine. In this case, the entropy of mixing per mole is double what it is for MgFeO because there are two Avogadro's number of sites in the structure. We double the number of sites, we've doubled Na, it's Na times 2, so we need to double the entropy of mixing. So the entropy of mixing is going to be minus 2RT into XFE ln XFE plus XMG ln XMG. Okay, so it's the same expression as before, but multiplied by 2 because there are 2 times Avogadro's number of sites in the structure. And when we go through all the differentiation, I'm not going to do, it's just double. We find that the mu of Fe2SO4 is equal to the free energy of Fe2SO4 pure plus 2 RT ln XFE. Okay. So we get double the amount of entropy of mixing because there are double the number of sites per mole in the formula unit. So in this case, remembering that 2 log x is the same as log x squared, the activity of Fe2SO4 is going to equal XFE squared. We just shove that up there, like so. And so on. So in general, the activity, if we take the standard state to be the pure phase at the pressure and temperature of interest, then the activity is going to be the mole fraction of the component we're interested in squared. All right, so that's what we're going to do in the practical. We're going to take the standard states to be the free energies of the pure phases, which I give you, and then we'll adjust the chemical potentials based on this. And there is one additional little wrinkle here, and that is, let's suppose we take a reaction Okay, the last thing that I wanted to talk about is putting all of this stuff on mixing into a thermodynamic calculation. And let's take an example. Let's take this reaction that we talked about the other day. Fayolite plus quartz goes to ferrocyanide. Now, as we've already said, magnesium and iron-bearing silicates tend to have a lot of magnesium in them as well. And we know that at equilibrium, delta G equals 0. And that equals twice the chemical potential of FeSiO3 minus the chemical potential of Fe2SO4 minus the chemical potential of SO2. That's quartz, that's in fayolite, and that's in ferrocyanide. So now we make the substitution mu equals mu 0 plus RT ln A. So 0 then equals 2 mu 0 FeSO3 plus RT ln A FeSO3 minus mu 0 Fe2SO4 minus RT ln A Fe2SO4 minus mu 0 SO2 minus RT ln A SO2. So fayolite, quartz, ferrocyanide. So what we do now is we collect the mu 0 terms on one side and the activity terms on the other. And we find that 2 mu 0 FeSO3 minus mu 0 SiO2 minus mu 0 Fe2SO4 is equal to minus RT ln activity of FeSiO3. Someone didn't point out that should be a 2 there. There are 2 moles of FeSiO3 in the reaction. That's squared because there's 2 moles there. Put the 2 up there. Divided by the activity of Fe2SO4 times the activity of SO2 . Okay, so what I've done, I've collected the Ln terms together on that side because I've switched sides, but anyway, and I've collected the mu 0 terms together. And that is the standard state free energy change of the reaction, delta G0. So this is the free energy change of the compounds in their standard state. So these are the free energy change of the pure compounds. And that equals minus RT times that lot. And this here is known as the equilibrium constant, K. So delta G0 is minus RT ln K. And what we'll be doing in the practical is we'll be putting standard state free energies, which will be delta H0 minus T delta S0 plus P minus 1 delta V0 for solids. Okay, so this will be the values for the pure solid, and we'll be putting in appropriate compositioning terms for the activities. All right, that'll do.